Mr. DeVellis here, back from Math Muscle. Just picking up on example 15 that was done on a prior video that whose point was really to help classify points of inflection. That's what this video is about. So as you can see at the beginning of the annotations that we've done the first derivative, which was from the prior video, and then for points of inflection we have to do the second derivative and set that equal to 0, which is what you can see here. By common factoring, we end up with the product of the common factor of 12 times a trinomial, 3x squared minus 8x minus 4. There are various ways of factoring a trinomial, but the way that's shown here in the video is decomposition. If you need video support for decomposition, there are plenty of decomposition or other factoring methods for trinomials on YouTube. Feel free to investigate that if you need more practice. But having done the trinomial factorization, we end up with two roots, x equals 2 and x equals 2/3, and those correspond to points of inflection. So you can see by the highlighting that we've put them on a sign diagram, much like we did with the first derivative stationary points. We're doing the same with our second derivative points of inflection. From there we select test points, much like we did with the first derivative. So we selected x equals 0 on the left hand interval, x equals 1 in the middle interval, and x equals 3 on the far right interval. And then we substituted those particular test points into the second derivative. And really, all we're really interested in is whether they're positive or negative, the answers. Not so much what the actual values are, but more so whether they're positive or negative. And once we've done that, we'll do the first one together. We'll just highlight that. For the first derivative, when x is 0, I'm using the factored version, which is a lot easier. So this is the factored version right here of the second derivative, which will allow us to determine the sign easier. So we have 12, which is always positive. 0 minus 2 is negative 2. 3 times 0 minus 2 is negative 2. So we have a positive times a negative, which in fact will be a positive. So our second derivative in that interval will always be positive, which implies the original function will be concave up. Using the same logic and the same process, we did the same thing for each of the corresponding intervals. And we found that we have the second derivative is negative in the middle interval, which corresponds to concavity that's down for the original function. And using similar logic again, for the right hand side interval, we have positive second derivative, which means concavity is up. So it asks us to classify those points of inflection. You'll recall from part A of the video that's on my channel that x equals 0 and x equals 2 were stationary points. So classifying the points of inflection, some of the, well, let's look at our particular example. We have x equals 2/3. That is only an inflection point. It is non-stationary. As you can see, it's neither x equals 0 nor is it x equals 2. However, x equals 2 is an inflection point, but it's also a stationary point. So therefore, the classification will be x equals 2 as a stationary inflection point. And that's where that notation and that terminology rather comes from. And lastly, part D is find intervals where the function is concave up or down. Well, thanks to our sign diagram we did earlier, we noticed that the original function is concave up from negative infinity to 2/3, and we've also know that from 2/3 to 2 and from 2 to positive infinity that the original function is concave down. We're going to pull both those videos together momentarily and create a third video that actually sketches the functions with the features that we found. Thanks for watching. Be sure to subscribe if you haven't done so already.